Hello everyone, my name is Matthew Frick. I am a graduate student at the University of New Mexico and a programmer for the Swarmathon competition. Once you've visited our GitHub repository and followed the README instructions for downloading, setting up your environment, and compiling the code, you'll be able to go to a shell and type run.sh to start the program. And you'll use this software for monitoring, controlling the rovers, the physical rovers and simulated rovers. In this demo, we're going to start by creating a simulation. There are some options to select here. I'm going to select a final round, which means 6 rovers, and a power law distribution of targets. Press Build Simulation when you're ready, and it will set everything up for you. The gazebo interface is finished starting up here. Here's a visualization of our 6 rovers and the search environment. These surface textures on the ground here are taken from the parking lot that the physical rovers will search at Kennedy Space Center. So I'm going to select one of these rovers over on the left. If you had physical rovers and you connected them, they would show up here as well. Here are our 6 simulated rovers. And here's our sensory output from this rover. This is the map showing GPS data in red, encoded data in green, and the Kalman filter combination in white. So I can drive this rover around manually with the keyboard or with a joystick if you have one. Let's take a look at one of his buddies. Yeah. Okay, but to have them search autonomously, we click the All Autonomous button. And the rovers begin searching for the power law distribution of tags that we selected. The targets in this simulation are April tags. Each one is unique, and they're allocated among different size clusters. Here's a rover who saw a April tag and is returning back to the center, to the collection disk, to record that he found a tag, or she found a tag. The arena for the final round is quite large. Preliminary rounds have 3 rovers and a smaller arena. And we can see the rovers have already found 9 tags. This simulation is running at about 3 times real speed. So 21 minutes has passed already in just 5 minutes of physical time. Let's take a closer look at the interface and the gazebo client. So this time I'm going to select a preliminary round, so smaller and with 3 rovers, and a clustered distribution of targets. And just for fun, let's choose a different texture for the ground. Let's take a closer look at the sensor display for these rovers. I'm going to set them all searching. When a rover sees an April tag, it uses the camera to detect that an April tag has been found. The map here shows where the rover believes it has been. So it has this sense of where it is in the world based on a combination of the GPS, the wheel encoders, and the IMU. You can see that the GPS, these red dots, are kind of noisy. The encoders are much more accurate, but they are susceptible to drift. In fact, we can model this in the simulation. So here's the IMU drift, for example, 0.01, and the GPS noise that we've introduced. So it's worth emphasizing that even if you have physical rovers, you should spend some time running simulations as well, because you'll be able to do many more experiments in simulation at this 6 times speed, for example, than you will with the real rovers. And if you are able to set the noise and the drift in simulation to match that in the rovers, you'll have a pretty high fidelity simulation. The code we provided for you allows you to detect tags using the camera, keep track of your position with encoders and GPS and IMU, and to detect collisions using the ultrasound sensors. There are 3 ultrasound sensors, one on the right, one on the left, one in the center. And the orientation of the rover can be determined and is visualized with this IMU frame here. This is a real physics simulator, so we can do fun things. For example, I can pause the simulation here, select a rover, this is Bartik, and I'm going to have some fun torturing Bartik a little bit. So let's move it on its side. This is so I can show you how the IMU sensor is affected by pitch and roll. So here's Bartik, who's spinning around on its wheels now. So you might want to use this IMU sensor to determine when a rover is flipping over or is run into an obstacle, that sort of thing. But let's help Bartik back onto its feet. There we go. And it goes about collecting tags more. Some more. So at this point, they've collected 7 tags and observed 29 or 31, 32 tags now, and they've had 5,000 obstacle calls. So detected tags means the number of tags that have appeared somewhere in the camera and have been observed as valid April tags by the rover. Collected tags are tags that have been returned to the nest. Now, of course, they don't actually pick up tags, so it's sort of a virtual return. It means it's seen a tag, selected it for return, and successfully reached the center of the map. In robotics, a very important measure of success for your algorithms are the number of collisions that occur. Collision calls tend to be expensive. It means the rover has to stop gathering and handle getting around the obstacle that's detected. So we count the number of collisions that happen. And this is just a count of how many times did the ultrasound sensor say that there was an object within about 10 centimeters of the rover. You can control the speed and fidelity of your simulation by changing parameters to the ODE solver that calculates collisions and the physics of the simulation. The parameter we've changed most is the max step size. This is how long in seconds between solver updates. So the larger this number, the faster the simulation will go, but the less realistic it will be. I'm going to stop here and move on to the source code and how you can implement your own search logic. The easiest way to understand how we've organized the code is to understand how ROS itself works. So each package here is compiled into a separate executable or library that gets run in its own process. These processes run in parallel, independently, and they communicate with each other via message passing. So the ROS paradigm is to create topics. Different processes will publish data on topics and receive data by subscribing to topics. So we're going to start RQT, which has a host of helpful plugins. Right now we're running the Topics Monitor plugin. This is a list of all the topics that have been created by ROS. And you can see that there are a number of topics associated with each rover. So this string is the topic name. For example, here is a topic published by Antonelli showing IMU data. So if I check it, it'll start recording the IMU data that's being broadcast by that rover. I'm going to set these rovers going again so that you can see the data change. And now we can see this get updated because the IMU sensors are populating this topic with information about the pose, the velocity, the orientation. There are also some global topics. Here's a joystick topic. This is how we communicate information from the joystick driver to the mobility class, if you want to drive the rover around. Here is the ROS out topic, which is particularly important because when you want to publish or print debugging statements, you'll call ROS message or ROS error or ROS info. And ROS info displays its data here. So you can see ROS out is already printing some debug statements that we have in our code. I want to show you the targets collected topic. This will print the April tag ID of the last tag discovered and collected. And you can see it's a global topic. So this is published by all rovers under the same topic. So it's a collective statistic. So when you're looking at the source code and you see publish statements and subscribe statements, now you know what they're doing. They're gathering data from these topics and publishing data on these topics. An easier way to get output from something like ROS out. Let's open a new terminal here. Is to use ROS topic echo and then ROS out. I find this to be an easier way of reading the output from a topic than always looking in the GUI. We've divided up the source code for the competition into ROS packages. So if you look within the rover workspace, under the source subdirectory, you'll see a number of packages. So abridge, gazebo plugins, mobility. And I'll go through each of these and explain what they're intended to do. Let's start with mobility. So mobility is the logic that controls what the rover does, the rover's behavior. Every package has a cmakelists.txt file. This is the make file that allows you to build the software. So in ROS, each of these packages runs independently and communicates through message passing interfaces. Those message passing interfaces are called topics, and I'll go into more detail in a little while about topics. You shouldn't need to modify the cmakelists.txt files unless you're adding libraries that you're going to use to help you with your code. What you will modify is mobility.cpp. So this is all in C++. You can write your packages in Python if you so desire. We've written everything in C++. So in ROS, there's a concept of publishers and subscribers. When one package wants to talk to another package, it publishes messages on a topic, and another package will subscribe to that topic and receive messages from that topic. So here are functions that get called whenever a message is received on a particular topic. Here is a function that describes the joystick handler, the target handler. So when a target is detected by a separate package, a message is broadcast and received by the mobility package. Let's take a look at one of those callback handlers. So here's the obstacle handler. It receives a message here. And in this case, it very simply turns if the obstacle handler says that there's an obstacle on the left or on the right. So the rover turns to avoid the obstacle. This sample code we've given you that performs a random search, finds tags, and returns them to the center is organized as a state machine. So a state machine is just a way of writing code where there's a state, there's a current state that says, is the rover searching? Is it carrying a tag back to the nest? And there are transitions from state to state depending on what the rover sees, what the rover encounters. And here it's organized simply as a case statement with some if logic. Here's an example of a state where the rover is rotating. Rotate left, rotate right. This is where you'll write your own logic. You can organize it as a state machine, you can organize it some other way, but this is probably where you'll spend most of your time determining the best way of searching for tags. The obstacle detection package is extremely simple. It handles messages broadcast by a bridge that pass on information from the sonar sensors. So here's a callback called sonar handler that takes one of those messages and simply reports to mobility, the mobility package, where the collision is on the left or on the right. So when it determines whether the collision is on the left or the right, it publishes that message on the obstacle mode topic. So here's an example of creating a publisher. We're advertising that there will be messages on this topic. The topic name is the rover name / obstacle. One of the most important sensors on the rover is the camera. Camera data is processed in the target detection package, and is used to detect April tags using an April tag library that we have. The include file has a lot of stuff going on, but the source file are relatively simple. There's a camera processing source file, target detection. There's an opportunity here, if you would like, to try and improve the performance of the rover by enhancing the target detection. But you can also use the camera for other things. You might use it, for example, to calibrate noisy sensors when you are near a wall or when you've reached the target collection point. The rovers consist of two hardware computation units. The Arduino board for processing and interfacing with low-level sensors, etc., and the motors, and an Intel NUC for higher-level processing. The interface between the Intel NUC and the Arduino is in a bridge package. So this is a driver for the USB serial connection to the Arduino. So you can see this sends basic strings over USB to the Arduino in order to give it low-level commands like set the speed of the motors, receive data from the sonar and the IMU, etc. One package that exists purely in order to interface with simulation is the Gazebo plugin. Right now we use the Gazebo plugin only to set the initial speed of simulation. So this line right here, where we set max step size to 0.01, sets the default step size. You can change that to go higher or lower. We found 0.01 to be about as fast as we can go without getting artifacts and crashes in the Gazebo simulator. But see if you can get it to go faster. If you do have trouble, then perhaps lowering this number to make the simulation be higher fidelity would be a good idea. This compiles into a library that is used by Gazebo in its world file. So here's the Swarmathon world file. Here's the library name that gets compiled. So when the world is created, it interfaces with this library. You might find other things in the physics simulation you can change from within the Gazebo plugin. And particularly, it's a place where you can create things like timers. So if you want to automatically time your simulations, you will be able to make a call to the simulated time functions defined in the Gazebo plugin library, and automatically stop your simulation when it reaches a certain time. The software provided includes simulation model files under the simulation directory. The majority of these directories contain information about the April tags. They also define the barriers in the simulation, the ground textures, and the rovers. So let's take a look at this rover. It's defined by mesh files. These are DAE files, which is a commonly used standard for designing models. And a model SDF that contains information on how to put all the mesh files together, how to set their bounding boxes, how to set collisions, And of particular interest is how to set error. So here's an example of an ultrasound sensor with Gaussian noise set to 0.005. So it's useful to be able to introduce error into sensors to make them more realistic and match your observations of the hardware rovers so that you get more out of your simulations. Let's take a look at the camera noise. So here's the camera joint linked to the camera sensor object. You can see we set the resolution to match the hardware resolution on the real rovers, the format of the images, and here we set the Gaussian noise to have a mean of 0 and a standard deviation of 0.07. So this would have an impact on how often you miss April tags, for example. The skid steer drive controller is the source of encoder data for the simulation. And here you can set things such as drift and other kinds of noise. Now I'd like to give you a little tour of the GUI. So here's the GUI. You remember the map and the camera, the ultrasound sensors, and the IMU pose visualization. We use a tool called Qt Creator. The GUI is written in a C++ add-on called Qt from Nokia. It's freely available. And the Qt IDE just sets up a really nice environment for taking a look at this GUI code. Right now it's parsing the CMake list file. We've organized the GUI into classes. One nice thing about the IDE is I can click on Rover GUI plugin, and we get a WYSIWYG layout for the different frames where we can display data. So each of these frames is drawable from Qt and allows me to write a class that corresponds to each of those frames. So, for example, here's the camera frame. And really all it does is have a paint event that draws the images it receives and a set image function. So here's the paint event. It draws some text if there's no image, and otherwise is extremely simple. It just takes advantage of this draw image function that's already provided for us. Some of the other frames are a little more complicated. For example, the IMU frame this paint event is a little more complicated, has a number of projections because we're trying to draw into a 3D space, and so we have to define a camera view function that takes 3D data and projects it onto a 2D plane. And we have to handle quaternions, which is how ROS communicates pose information. The map frame is also a little more complicated, but only because of the number of elements it has to draw onto the screen. There are two other important classes, apart from the sensor visualization classes. The Gazebo Sim Manager is our interface into the Gazebo simulation. And the way we've organized it is that it simply makes use of command line calls to Gazebo to create objects, destroy objects. And it spawns a new process for each of those. So it starts a process, makes some terminal commands, some shell commands, and then kills that process. The Rover GUI plugin is the top-level class that organizes everything else into one coherent structure. It handles much of the logic of tying buttons together to functionality, receiving information on topics, and passing them on to the appropriate sensor, that sort of thing. So for here example, joystick messages are received, it checks for the dead zone, and then passes the joystick message on to the motility class to move the rovers around, and also updates the GUI to show what was the value received from the joystick driver. So just to give you a taste, I'm going to search for the add rover command, which shows up in the Rover GUI plugin inside build simulation button event handler. So the Qt GUI is also a message passing paradigm. It receives messages from GUI elements and then calls these handlers to process them, just like ROS does with broadcasting on topics and receiving and calling event handlers in the subscriber code. So here's where we create some rovers. So when that button is pressed, we create the right number of rovers based on whether the radio button final or preliminary is checked. And this sim manager is the Gazebo sim manager object. So let's go and see what those processes do. The function implementation takes a rover name and an XYZ position. And there's a wrapper function that also can take the orientation of the rover, the rotation, etc. So we create a queue process, pass in this string that we build from the input arguments, execute that string, wait for the process to finish building the rover on the Gazebo end, and then close and destroy that process. So this is just a brief introduction to how the GUI is organized, but I hope people will modify it if they want to add functionality, timers for example. So that about covers it for the code walkthrough. I hope I've at least given you a high-level view of how we've organized things, and you feel ready to start writing your own code and modifying what we've given you. I would like to point out one logistics aspect with regard to the competition. If you have hardware rovers, you'll probably want to modify almost all these packages, especially the simulation models, to try and get the error to match what you observe in your hardware, so that you can get the most out of your simulations. If you are part of the simulation competition, you should only submit changes in mobility, the obstacle detection package, and in the target detection package. Everything else on competition day will be default. So don't change your models, don't change the Gazebo physics properties, because they won't be used by us on the competition day. Okay. As you're going through this code, if you find any bugs or anything that seems odd, Feel free to ask on the forums that we've set up, to submit issues in GitHub so that we can fix any bugs that you find. We'd also be happy to hear about feature requests, so we can add things for you to use. And even more happy if you implement those features yourselves for your own use and share them among other teams, and let us know about the great improvements you've made to the code that we've written so far. All right, thank you very much and have a great competition. Bye-bye.